Welcome. In this video, we're going to look at some other methodologies we can use to solve systems of equations when graphing doesn't necessarily work. And in fact, most of the time, graphing is not the most helpful approach because you never know when you're going to end up with fractional solutions or solutions that just lie way outside the graph that you're using. So technology can help us in that way in using a graphing approach, but there's algebraic methods we can use as well. So some systems have fractional outcomes, things that are just not going to be really uncovered very well using a typical graph. And so the two different methods we're going to look at is the substitution method in this video. In the next video, we'll be looking at the elimination, sometimes also called the addition method. So using substitution, this is kind of the first approach. Both substitution and elimination have benefits. We're going to look at when one might be more appropriate to use than another. But in terms of steps, when we use the substitution method, the first thing we want to do is pick one of the equations and one of the variables that we're going to solve that equation for. And what we want to look for in the two equations that we have, generally it's two, is to pick the equation that has a variable term that has a 1 as a coefficient, okay? And generally we don't even see the 1, right? 1 times x is just written as x, or 1 times y is just written as y. So we want to look for, within our system of equations, which equation has a term, a variable term that just has a 1 as a coefficient. That's the one we generally want to solve for. So that's we're going to solve, meaning we're going to get all the other terms and constants to the other side. We're just going to isolate that. And then we're going to take the expression that that variable is equal to, and we're going to substitute it into the same variable in our other equation. Right? So we'll have x equals, and then this expression on the other side, or y equals and an expression on the other side. We're going to take that expression and substitute it into that variable in the other equation. And then what that does is it essentially gets rid of that particular variable, and we only have one variable left with a bunch of numbers. So we're going to solve for that remaining variable, and with that we have half our solution, because remember our solution is actually an x and a y, so it's an ordered pair. Once we have one of those numbers, we're going to substitute that number into one of the equations, doesn't matter which one, and solve it for the remaining variable, okay? And there's the other half. So let's actually go through this and take a look at it. Okay, so let's take a look at these two systems. You'll notice that this one is written actually in the slope-intercept form, and this is actually written in standard form, where we have two variable terms on one side and the constant is over here on the other side. That's called standard form. I'm going to write this up here because you may hear me referencing it, but standard form is generally ax plus by equal to c, meaning the two variable terms are on either side of the equation, on the same side of the equation, and the constant value is over on the other side. Regardless, that doesn't really matter in this situation. I just want to point that out. And I also want to point out that the first equation is actually already solved for one of the variables. When we say solve for a variable, that means get it to one side of the equation and everything else to the other side. So get that variable by itself. And so we have an expression here for y. And my first step in solving this using substitution is to substitute that value in for y. So I'm going to rewrite this, 2x plus 5. Again, we'll put parentheses where the variable y was, equal to 16. And now I'm going to substitute that in there, 2x plus 8, because we were told that 2x plus 8 was equivalent to y. So putting that in there, we can now actually, we've eliminated, even though this isn't the elimination method, but we've eliminated y by substituting the expression involving x. So now I can solve this for x. I have 2x plus 10x plus 40 equals 16. Combine my like terms, so 2x's plus 10x's, that's 12x's, plus 40 equal to 16. And then we'll move 40 to the other side. So I get 12x is equal to negative 24. Divide both sides by 12. X is equal to negative 2. So I have half of my solution for this equation, negative 2. That's my x. The solution to a system of equation is an ordered pair, so we also need to know the value for y. But since I have negative 2 here, I go back to either of these two equations, substitute that in there, and that gives me negative 4 plus 8, which is 4. And so I have my other number there as the solution, negative 2, 4. If we want to check it, we can see if it works in the other equation as well. Oops. And so that gives me negative 4 plus 5y is equal to 16. Adding 4 to both sides to get rid of the negative 4. 5y is equal to 20 then. And dividing both sides by 5, we get y is equal to 4. So both of them gave me 4. I can feel confident that that really is the correct answer there. Let's try it again. So again, we're given two equations here. These are both in standard form, meaning the x and y terms are on the same side and the constants are on the other. And this one's not solved for anything, but I'm going to look and find the one here. This x has a 1 as a coefficient. It's 1x. So I'm going to solve that one for x by adding 3y to both sides. So by adding 3y to both sides, I get x is equal to 26 plus 3y, or 3y plus 26, however you wish to write that. And now that I have that, I now have an expression that I can substitute in for x in the other equation. So we're taking out x this time, putting a parenthesis there. So, and then we'll substitute that expression, 26 plus 3y. And now we have an equation that just involves y, so we can substitute, or we can solve this for y. We'll distribute the 3 here, so 3 times 26 is 78 plus 9y minus 2y equaling 15. And we can combine these two terms, so that gives me 7y, 78, 15. And then we'll get the constant to the other side by subtracting 78. That gives me negative 63. And then we have 7y over here. Dividing both sides by 7, we get y is equal to 9, negative 9. So notice what I have here is I have half of my, again, solution that I'm after. Now, plugging this back into my original equation, what's kind of helpful a lot of times is to go back to the one where you solved it for the other variable, because that it's written such that x is already by itself. So putting it in there, I have 26 plus 3 times, and there we have negative 9. So that's 26 plus negative 27. 9 times 3 is 27. And if we add those together, we get negative 1. And so my solution is negative 1, 9. That is the ordered pair where these two equations intersect with each other. Okay, another example here I want to go through. Here we actually have a host of different variables we can solve for. So I'm just going to take one of them. We'll take the first one. We'll move y to the other side. So that gives me x is equal to negative 1 minus y. And with that, I'm going to substitute that in to this equation here. Oops, I'm solving not for y, but for x. And so I rewrite that, -1 minus y. And then we have plus y equals 3. Okay, well, there's nothing to distribute there, so I can just kind of ignore the parentheses. They don't serve much purpose, except for my original, putting them there in place of x. And combining my like terms, I end up with -1, -y plus y. That becomes 0. So I have -1 plus 0 equals 3. In other words, -1 equals 3. So unfortunately, what happened here is my y values disappeared. And I'm left with this statement that -1 is equal to 3, which we know is not a true statement. That's a false statement. What does that tell me about my solutions? This is one of those weird scenarios that occur. So since they're kind of different and weird, that's what I call them. I call them the weird scenarios or weird situations. And basically the weird situations happen when all the variables cancel out. And we're generally left with one or two possible scenarios. The first one is that we're like what we had there is we end up with a false statement. There we had -1 was equal to, I believe, 3. But we could have 0 equal to 3 or what have you. In that case, what that's telling us is we have two independent and inconsistent equations. In other words, they're parallel lines that don't intersect. So they're independent, meaning they're different equations, they're different lines. Inconsistent means they don't share any points. And so these are two parallel lines, and since parallel lines never intersect, at least according to Euclidean geometry, we would say there's no solutions for this set. Because the intersection point is what we're looking for. If we were left with a true statement, like 3 is equal to 3 or 0 is equal to 0, those are weird. Yeah, all the variables disappeared, but we have these true statements. Then what that means is these two lines are the same line. So they're consistent, they have at least one solution, and in fact, they're dependent. They're not independent of each other. They are, in fact, the same line. And in that case, all the points along that line are solutions to that system. In our previous example here, we ended up with a false statement. And so my solution for this system of equations is that there is no solutions for that system. You can symbolize the empty set also, 0 with a slash through it. That also means nil, the empty set, no solutions. Looking at one more example here, finding the solution to this system. So the one variable that's by itself that we can sort of isolate here is the y there. So I'm going to subtract 2x to both sides. So that gives me, notice that it's a -y. So -y is equal to 3 minus 2x. It's important to remember that subtraction becomes negative because we actually need to get rid of it. That's a -1. So to get rid of it, we divide both sides by -1. That takes -1 into both terms, or divides both terms by that. So y is basically, they both become opposite signs. So instead of +3, I have -3, and -1 divided into -2x makes it +2x. All right, so I have my expression for y, which I'm going to substitute into one of the other two equations. So this gives me -6x plus 3 parentheses equals -9. And substituting my expression in there, -3 plus 2x. And now we can distribute and simplify, solve this for x. -6x plus -9 minus 6x equals -9. Notice that my, let's see, this is actually, positive 6x. I have positive 3 times positive 2. So -6 and +6 eliminate, and I'm left with -9 equal to -9, which is a true statement. That means graphically that these are two lines on top of each other, essentially. They're both the same equation. And so we have infinite solutions for this set. They're both along the line 2x minus y equal to 3. I just named one of those two equations there. If you'll notice, I'm going to write this up here, 2x minus y equal to 3. Sometimes you can spot these before you go through this whole process. Save yourself a little bit of time. These look very different, right? They look like completely different equations, but in actuality, the first one or the second one is a multiple of the first one. If I take the first one and multiply it by -3 to all terms on both sides of the equation, that gives me -6x. -3 times -y is +3y, and -3 times +3 is -9. So the second equation is simply a multiple of the first. That means they're just the same equation. They just look different because we threw an extra multiplication in there. Let me take you right back to this other one here. This is the one where we had no solutions. Notice that it's x plus y equal to -1 and x plus y equal to 3. This one wasn't even disguising itself very much. Notice that they're both, on the left-hand side, a sum of x and y. And it's a sum of two variables, x and y, which would represent the same numbers, but coming out to different sums. So there's no two numbers in existence that I could add together, get -1, and then I turn around and re-add them together and get 3, right? That's nonsensical. It doesn't work. And so therefore, we can see that there is not going to be a solution here. These are two similar equations. They have the same slopes. And we can tell that because the coefficients in front of x and y are the same in this particular case. But their sums are different. And so that means they have different y-intercepts, and hence they're going to be not the same line. Okay, now I want to look at a particular story problem that we have in mathematics that a system of equations is pretty much perfect for solving. Otherwise, it can be a very tricky problem without a system of equation. And you've probably possibly have seen problems like this, but the idea is we're trying to combine two solutions with different percentages of purity together to get a certain other solution, a third solution, with a certain percentage purity. So in other words, in this particular problem, let's go ahead and read it. And a lot of times you have to read these several times. But a chemist needs a 100 millimeter solution of a 30% acid solution. She has a 10% acid solution and a 40% acid solution available. So notice that she has kind of a more diluted solution, the 10%, and a more concentrated solution, right? A higher percentage of it is actually acid. So she wants to combine the more concentrated one with a more diluted one to get something that's just a little less acidic, that's only 30% acidic. And the question is, how much of each should she combine to make that 30% acid solution? She needs specifically 100 milliliters of it. So, now in this problem, first of all, we're doing systems of equations. We know that we can use two different variables here, which actually makes it much more simple for us. And when you think about what your variables need to be, this is probably the most important step in doing these equations. We're wanting to know, and this says music, obviously that should be how much. Must have had there's no music in this problem. That must have been a correction that I didn't want corrected. So how much of each should she combine? So we're looking for a quantity of each. Now the quantities in this case are being measured in milliliters. So I'm just going to say X is going to equal the milliliters of the 30% solution. And then the Y will be my more, well, I'm not sure why I did it this way. Actually, no, I'm sorry. We don't want the 30 solution. Let me go back. 30 is the one I want in the very end. We want the other two. So we're going to take the more diluted, so the 10% solution, and then Y will be the milliliters of the 40% solution that I need. There we go. And we're going to do a certain combination, the more concentrated with the more diluted. There's two equations that we can get from what we have here. First, the easy one is just the combination of X plus Y. Because I know that I want 100 milliliters, right? So I know that however many milliliters of this I have, combined with however many milliliters I have of the Y, I know that I'm going to get a 100 milliliter solution when I'm done, or that's what I want at least. All right, the second one I'm going to put in terms of the acidity level and how much acid we have in our solution. So we're wanting in the very end a 30% acid solution, and we have 100 milliliters. So if I take 30% or 0.30 of 100 milliliters, that tells me that 30 of those milliliters are going to be pure acid, right? Well, we're going to look at the acid as well with the milliliters that we have represented with X and Y. In other words, X is representing the 10% solution. So I'm going to go 10% of X, however many milliliters, plus 40% of Y should give me 30% of 100, giving me 30. All right. So let's just simplify this. Those were two numbers, so we can actually carry that out over here. But these are my two things. The first one is giving it to me in just pure milliliter form. The second equation is the acid form, basically. We're taking the percent purity times the amount plus the percent purity times the amount of the other, giving me hopefully 30 milliliters of pure acid in my mixture. All right, this gives me two different equations, and I can now use substitution. Let's take Y to the other side. We'll rewrite this for X. X is equal to 100 minus Y, which there's my expression for Y. We can substitute over here. So 0.10X plus 0.40 times 100 minus Y equals 30. And distributing this out. Oh, I substituted in the wrong thing. Okay, let's take that back a little bit. And let's put it into the right one. This was supposed to go in for X. So let's keep it going. So 10% times 100 minus Y plus 0.40 times Y equals 30. All right. I can tell I made a mistake there because I still had an X and I had a Y, so something was off there. All right, distributing, that gives me 10 minus 0.10Y plus 0.40Y equaling 30. I can combine the two Y terms. That's a negative 0.10, so that gives me 10 minus or plus 0.30, because negative 0.10 plus 0.40Y gives me 30. And then we subtract 10 on both sides. A variable term by itself. And now we divide both sides by 0.30. Y is then equal to, gives me 66.67. So what is that? That's 66.67 of a 40% milliliter solution. So how much do I need of the other, the 10% solution? Let's go back to my original thing. I'm going to substitute this y in for the first one, which is just a simpler one. All right, put that in there for the y. And if I subtract 66.67 on both sides, we get x is equal to 33.33 milliliters. All right, so we need 33.33 milliliters of the 10% solution mixed with 66.67 milliliters of the 40% solution. And there we have it, a mixture problem.